Yesterday's thermal conductivity instruments typically limit characterization to a narrow range of sample materials. The samples are often forced to adapt to the instrument's rigid requirements, rather than the instrument adapting to the sample and application needs. Trident, by industry leader C-Therm, represents a new paradigm in thermal conductivity measurement, delivering three of the most powerful transient methods in one instrument. It's better to have options. Built on C-Therm's reputation for world-class thermal conductivity instruments, Trident is dynamic and satisfies the most prominent ASTM and ISO industry standards. It combines the precision of MTPS with the flexibility of TPS and the robustness of TLS, all in one modular package. These options support a wide range of applications without sacrificing ease of use. Trident meets the needs of today's labs and is future-proof for the challenges of tomorrow. The MTPS, Modified Transient Plane Source method, employs a single-sided sensor to directly measure the thermal conductivity and effusivity of materials. The method features the highest precision and sensitivity, providing accurate test results in seconds. It offers the maximum versatility for the non-destructive testing of solids, liquids, powders, and pastes. It is adaptable for high pressure, broad temperature ranges, and environmental conditions. No regression analysis is required. MTPS is the choice method for situations where reproducibility amongst multiple users matters. With a double-sided sensor available in different sizes, the Flex TPS Transient Plane Source method provides researchers the greatest flexibility over experimental parameters, including timing and power. It is recommended for more experienced users with specialty slab, anisotropy, and thin film modules available. With no contact agent required, the hot disk-style TPS sensor is ideally suited for polymers, compacted geological samples, metals, concrete, and asphalt. Flex TPS is ideal for experienced researchers looking to push the boundaries in thermal conductivity. Sheathed in stainless steel, the TLS, Transient Line Source Needle method, offers maximum robustness in thermal conductivity testing. TLS is best suited for granular materials, polymer melts, soils, slurries, and gels. C-Therm software provides full data acquisition and analysis in one user interface, allowing full control of all three methods: intuitive, logical, easy. Trident reflects C-Therm's years of experience working exclusively to provide labs, researchers, and manufacturers with the very best in thermal conductivity measurement. C-Therm's products are globally distributed in over 65 countries around the world, with full local support. Trident. It's better to have options.
All right, good day, everybody. Apologies for the late start there. We were having some technical difficulties getting things set up, but with that being said, we'll jump right into our webinar here today. Get this shared on screen here. All right. So, welcome. Today, our webinar is titled Innovative Techniques for Accelerated Characterization of Polymer Composites. And I'm pleased to announce we have a guest speaker here today. Khalid Bokale from Labs Cubed. We'll be discussing some content with regards to tensile testing characterization. Also, my colleague Travis Parkman, Dr. Parkman, will be joining us near the end of the session to go over some applications in this space for DMA, dynamic mechanical analysis. So for those on the call here today, some housekeeping items. There is a chat box that you can make use of on the side of the platform. If there's any questions that you have throughout the presentation, please feel free to make use of that. We will reserve some time near the end of the session for a Q&A. Also, my colleague Landon, who is moderating the session here today, will be dropping in some various links as it relates to the content being presented here today. So all that being said, let's go jump right into it here. So I want to start out with a little bit of just an introduction to C-Therm. So C-Therm Technologies, really kind of our purpose statement, what we do on a day-to-day basis is simplifying thermal conductivity testing for the materials of tomorrow. Really, we are all focused on the thermal characterization side of these materials, but of course, they will also be looking at some various mechanical properties as well. So that little intro video that we played just to get things going, kind of introducing the Trident platform. This is the method that we will be really focusing on from the thermal conductivity side. Trident, it was developed as a modular platform. If you're new to C-Therm and a new instrument to you, it's a transient-based option for thermal conductivity characterization. Modular in its design, so really you can see there's different methods available, and it allows you to pick the one that's most suitable for the task at hand, depending on your materials, the application, testing conditions, etc. Today in particular, we'll be focusing on, I'll be highlighting two methods on the platform, the MTPS, the modified transient plane source, as well as the more traditional flex TPS or transient plane source. So we'll have some content on both of these options from a thermal conductivity side as we transition through the session here today. So just have this quote here, and it's really a representation of why and the reasoning behind Trident, how it was developed, and the modularity within. From Abraham Maslow, you can see here, when all you have is a hammer, everything looks like a nail. And of course, we relate this to the idea where if you have a method for thermal characterization, or really any testing method, it might be really good for a certain section or grouping of materials or testing conditions, but it doesn't necessarily mean it's going to work for everything out there. And, you know, all in all, one of the largest sources of poor data collection that we see on a regular basis is if you take one of these really good methods, but apply it in an area that it really wasn't designed for. So the idea, of course, here with Trident is allowing you to pick the best tool to really tackle what's in front of you at that given time. Now, if thermal conductivity is new to you and it's something that you're looking to develop or learn more about, of course, coming into this, there's a lot of information out there. This method selection guide, this is available as a free download on our website. It's a really nice free content piece that can give you some insight into the different methods that we offer here at C-Therm, as well as some of the other methods available in industry. Would definitely recommend taking a look there if it's something that you're interested in learning more about. And if you really want to take more of a measured next step, we do offer, of course, if you're interested in the instrument and would like a quote, we're happy to support that. But if you maybe want to go into a little bit more of a deeper dive, chat with us one-on-one, really go into your application and your testing requirements, we do offer technical consultations where you can meet with some folks here at C-Therm, discuss your interest. We can provide you some recommendations on how to go about testing some of these methods with these methods, and also even do a live system demonstration. We have a range of different materials to pick from, so we can find something that's really akin to the application that you're working in. And just wanted to end with a little client testimonial. We always like to promote what our clients are saying about us. It's really it's always nice to hear what they're using the instrument for, how they're liking it. We do have a range of testimonials available on our website. I just pulled one of these here today. They're talking about the use of the MTPS sensor being very popular in their lab for quick, reliable measurements. Also highlighting that they recently upgraded to have the TLS module. Again, these systems being modular, you might start with something, find in the future you need to add an additional capability, and it's very easy to do that. This was Jose Fonseca, who is a thermodynamics expert at Covestro. And at C-Therm, we also do work in collaboration with some, we do have partners for various other instrument techniques. One that's not as heavily focused on here today, but Rigaku Thermal Analysis, we represent them in North America, their line of DSC, STA, and TMA instrumentation. This is really complementary to a lot of the content that we'll be speaking to today, especially in the polymers characterization space. So definitely have some resources available for that side of things as well. And then, as I mentioned, my colleague, Dr. Parkman, will be discussing the dynamic mechanical analyzers from Metrovib, who are, of course, leaders in their field for these high-performance DMA systems. So that's going to kind of set the tone here. But going into some of the bulk of the presentation, I wanted to start out with a little bit of content on thermal conductivity. And again, we're going to be looking here at two of the methods and some different case examples there within. The first one, taking a look at, is the Modified Transient Plane Source, or MTPS. So this is C-Therm's proprietary sensor design. A few notes here you can see about this technique. It's a single-sided sensor design. This has some unique aspects with respect to some of the test setups and the testing capabilities. I have a few examples of that we'll go into here in a few minutes. In an R&D setting, the ability to test multiple samples, you might have a broad category of things that you're looking to run through. We do have among some of the fastest test times of any transient option available on this method in particular. Many of the folks that we work with that are in the R&D space or simply of needing high throughput to manage their workload, the MTPS is a really great option there. And it is quite versatile. If we're talking in the solid state, testing liquids, powders, pastes, there are different configurations available therein. So just a few little notes there on the MTPS. I wanted to give you a kind of a high-level principles of operation run through here. So, we won't go too deep into the weeds here today, but really just to give you a sense of how the measurement works and how you apply your samples for a test. So the single-sided interface design really allows the material that you're testing, you just put it over top of the sensor's active zone. There is a spiral heating element that covers that top portion. This is, of course, what's going to heat up and deliver that thermal input for the measurement itself. So as your sample is in contact here, deliver that pulse. As that's occurring, the system is simultaneously monitoring the change in temperature that occurs as a function of time. And you'll notice a similar aspect on that side to really any transient-based technique. It's we're applying some thermal input and monitoring that dynamic change that occurs. Of course, different materials will respond quite differently to that temperature increase as it relates to their thermal properties. The nice thing with the MTPS is that all of the settings for the measurement and all the data analysis that is done, this is handled automatically within the software package based on the calibration setting that is selected for the measurement. With this, essentially, it eliminates a lot of potential user bias that might be introduced in some other methods. It's a really great option if you have multiple folks in your lab all going to be operating the system. Really allows for consistent data across different users. The last thing I'll flag with the MTPS before moving forward here is just related to the guard ring. Now, the guard ring you can see pictured here, it essentially promotes a one-dimensional heat transfer into your sample. It does so by preventing that lateral heat loss from occurring. And essentially what this allows you as a user to do is have a directionality to your measurement. So it provides a controlled directional based measurement into the test material, which can be important if you are looking at materials that are perhaps anisotropic in nature. So this first example here, this is an area where we've seen quite a bit of traction, especially in the last few years. In the polymer space, especially anything that has a type of filler or an additive being introduced into the system, which is, frankly, most novel materials these days. The ability to detect and quantify the distribution and the evenness of that filler throughout the material is going to be really important, because you can load in your filler into your sample as much as you want, but if you're going to have really in non-ideal distribution like we're showing in this picture here, the end performance isn't going to be as really optimal for the heat dissipation side. You're going to get hot spots, things of that sort. But with the MTPS, because it's a relatively small active area, and again, a very quick measurement, it allows you to take the sensor, move it around at different locations on the sample, and really collect these spot measurements to do this type of mapping of the material. And then what we can do is, of course, correlate the resulting thermal conductivity values to things like the filler concentration, the internal structures, different defects that might be present, anything that's going to cause non-uniformity within the sample itself. So in this example we're showing here of, as you would expect, very large differences at each test spot, related to the fact that it's, of course, a very non-evenly distributed sample. But for something like this, more of a visual inspection would probably be sufficient, just based on looking at it. But when you are working with something that's maybe opaque in nature, a lot of TIMs, thermal interface materials that we work with, you're not able to detect this just based on visual inspection alone. Well, the MTPS can come in and be that type of check for you. So wanted to quickly touch on the measurement directionality aspects of anisotropy. This is something that is quite relevant to many of these materials that we do testing with and groups that we support. As I mentioned, with the MTPS, it has a controlled directionality, and it's really based on what position the sample is placed with respect to the sensor interface. So just in an example, if I had a cube type sample like this, I'd put it over top of the sensor. So let's say this bottom portion is in contact. Well, the measurement results that I'm going to be getting are going to be indicative of the Y direction here. Now, based on that idea, if your sample allows for it, what you can simply do is just rotate different sides in contact with that sensor interface, and then you can measure out those different directions within the material. So it allows you to get at that directional behavior within a bulk material simply by reorienting the sample on the sensor itself. In this case, a little data set here, in a similar idea to what we're talking about there with the measurement directionality, you can also do it in some instances where your samples might be a little too thin or too small. The example here of these, tensile bars, again, there's a lot of crossover between the material characterization that will be discussed here today. But a sample like this, the through plane measurement, you can see represented in that MTPS's active zone, perfectly sufficient. Just put one on top, take that measurement, be good to go. But to measure the in plane here, obviously these are way too thin to cover the sensor fully. So what you can actually do is stack a few of them up, clamp them together, and rotate them to get at that type of characterization. You can see the differences in the in-plane versus through-plane measurement of these samples. The materials that were tested in this case had a carbon-based additive, which was introducing some directionality into the material itself. So just a little case example of some of the material testing setups that can be done. Moving into the TPS. Now the TPS, the transient plane source, it's a little bit of an older method, still transient in nature. You can see here, it looks quite different from the MTPS. It's a double-sided sensor design. The way you go about testing with the TPS is a little bit different as well. But one of the unique aspects with the TPS in particular is we do have some unique advanced utility options available on the platform for TPS. And I'll aim to speak to some of those here in the following slides as well. Now, from a principles of operation standpoint, again, there's some similarities, but really some differences here between the different methods I'd like to highlight. The biggest one is in the sample setup. Because it's a double-sided interface, you're going to have two samples, one on top and one on bottom, to do your measurement. The other thing that's quite different is that there are no calibrations to pick from per se for this method. You will instead be manually defining the time and the power parameters for each test. So it puts a little bit more control on the testing process, puts it on the user to define for the testing. Once you've established your settings and you run your tests, we're still collecting that change in temperature as a function of time. Again, that's going to be similar for these different methods. But the added step with the TPS is the verification process that has to be done post-measurement. So there's a little bit more of a manual analysis that is required to go through and essentially validate the results, albeit that we do have a very, I'd say, well-optimized software, which really helps guide you along that process and provides you with feedback during the testing. But just to highlight, it does require a little bit more understanding and practice compared to the MTPS. Now, the more advanced functions within the TPS, it really relates to some specific material types. And for when we're talking about polymer characterization, really there's two that stand out. There is the anisotropy TPS utility as well as the thin films. So I wanted to just give a quick little example of each. We'll first take a look at anisotropy here. In the TPS function, anisotropy, so establishing a in versus a through plane measurement of a sample, it's done in a singular measurement. So unlike the MTPS, which is you'd be manually rotating the sample around, testing at different points, this is all done with one singular measurement on TPS. Now, it does require that within the software you manually input the specific heat capacities of CP and density. And again, when I was talking about Rigaku's product line, really the heat capacity being a key component for many of these characterizations. This is required, but essentially within the software package, you go through a very similar testing process as with your standard TPS, but what you get out at the end of the day is both the in and through plane direction. And again, it's important because these differences can be significant depending on the materials that you're working with, what's involved in the filler and their construction, etc. The other really unique aspect is the TPS thin film. So generally speaking, when we're talking about whether it's MTPS or TPS, the thickness requirement for many samples is at least 1 millimeter, sometimes upwards of 10 or more millimeters thick. It kind of ranges depending on the method used, the sample type, etc. But, there are these films that can be in the micron range, and how do we go about testing those? So with the thin films utility allows you really a direct way of assessing that without having to produce a thicker sample or stacking multiple up to create a minimum requirement. We can test samples down as low as about 10 microns in thickness. So it does allow you to test freestanding polymer-based films. You can see some example measured results here. And the testing setup involves a successive layering procedure with a backing material. So, I won't go into extreme detail with that, but if you did want to perhaps go into this, learn a little bit more, again, we're happy to go into those conversations one-on-one as needed. With the thin films options, just wanted to highlight that the TPS does come in different sensor sizes. They're available in a range from 6 to 30 millimeters. And again, this could relate to your sample sizes that you have available to work with, certain limitations in that regard. But in all cases, they provide very consistent measurements. The only thing that changes with the sensor usage is, of course, the sample requirements to cover the active zone. Thin films are also testing capabilities at elevated temperatures. We do quite a bit of work with folks that are maybe room temperature is really all you need, but there are scenarios, of course, where we need to go into that elevator, even the subambient temperature range to really understand what's going on. And in both cases, the sensors, MTPS, TPS, and the others available on the system do have those functions available. So definitely can go into some more advanced testing setups as needed. So again, I mentioned the Rigaku product line isn't going to be heavily featured, but I did want to include one quick video here before I pass it on. The Rigaku systems have a really unique aspect of their sample observation capability. This is a really nice tool that allows you to really tell a story. The data curves that you'll see in many DSCs, it's very similar. You have your temperature sweep, the response that's observed. But with Rigaku, they've added an actual camera that we can actually see what's going on with the sample as that process is running. And that allows for a few things. Really, it allows to, correlate what's happening within the material as it relates to what the data is telling you. But it can also inform on, is this peak here that you saw, is that noise or is that real? Sometimes it's hard to discern the differences. But when you can see the sample, it really allows you to fine tune the understanding of what the data is telling you. It's really great for people that are getting into DSC work, but also folks that have been doing it for a while. It just really allows you to make that connection very easily. So this video should be, let me see if that started here. Here we go. So just a really basic video, just a couple seconds, but it just kind of demonstrates what's going on. So we can see that heat flow curve that is generated as it's going through that temperature sweep, and then the real-time image of the sample that is being collected as the measurement is going. So we can see certain events are being flagged here. Again, certain changes might be occurring within the sample. So you can see it kind of starting to change here. And then the big noticeable one is, of course, right there where it goes into that full melted state. But again, just a little quick example I wanted to show, a really nice, unique aspect to Rigaku's systems. And with that, that brings me to the end of my section that I was hoping to run through with you all. So it's my pleasure to introduce Khalid on screen to continue some content here today with respect to their Labs Cube systems and tensile testing. So Khalid, welcome.
Hi, thanks for having me.
Awesome. I'll stop sharing here. There you go.
All right, I'll jump right on in. Let's see what we got here. All right, hi everyone. Jumping right on in, I'm going to kind of jump into talking about revolutionizing polymer development and the power of automation and AI and what it can really do to kind of speed up that process, whatever polymer you're working on. So quickly, a little bit about myself. My name is Khalid, co-founder of Labs Cube. So we started the company 7 years ago now, and time flies. We're getting into 8 years, and it came on the heels of my master's. So I did an undergrad in mechanical engineering. Then I did a master's in material development. So we were working on new structural adhesives for the automotive industry. So a lot of work in the lab. And after a lot of testing in the lab, I kind of started hating it. A lot of physical destructive testing, tensile testing, as we characterize materials for essentially putting them into their computer systems on the automotive side. So we did a lot of characterization in the lab. And so we kind of started the company with the idea of, can we take a lot of these very manual steps and automate them, but make it a really easy to use, affordable package? You don't have to buy a big robot. You don't have to, take a manual system and automate it. We're giving you the whole system, and it's just really easy to use. So that's kind of why we started the company. So what I'm going to go through is I'm going to give you a little bit of background about Labs Cube, show you the product and what we do. Then I'm going to talk about how to kind of prepare your lab for Industry 4.0. So the steps, the most successful steps that we've seen that people take to get to the point where they can have really good intelligence in terms of the systems they're building in. And then talking about the future of material development, where it's going to go, something we're working on called the Cube, which is kind of our long-term aim and goal, but I think it's pretty cool and it's starting to come together. So about Labs Cubed, we build automated testing equipment for tensile testing. We started out more in the elastomer rubber space, working with silicone companies. So Bridgestone is a customer, for example, Hexpol, if you know them, and they're out there, Airboss, some of those rubber compounders and rubber mixers. They buy our testing equipment, our lab equipment, place it into their quality labs most often than not, some in their R&D labs. And the goal is you take the manual single at a time tensile testing and put it all into an automated compact system. So it's automated tensile testing, as I said. Everything kind of happens with the tray, and I'll show you a quick video to give you an idea of how it works. You can test up to 15 samples in one tray. So effectively you preload them, put it in, press start, and walk away, and the system will automatically go through the process. Everything is there as per ASTM and ISO samples. We have customers that have been running for years on production side, hundreds of samples every day. And obviously for them, they have to be accredited labs and they have to follow ASTM standards because they share that data with their customers. So the machine is built around all the same standards. Hopefully you guys can see this video. I don't know if it's going to be choppy or not, but this is essentially how it works. You pull out the tray, place your samples into the tray. It can handle tensile samples, ASTM and ISO standard samples. It can handle tear samples in that same tray. Put it in, press start, and then the machine gets going, picks up a sample at a time, places it into the grips to be pulled. We'll then obviously break the sample as a tensile sample usually, or tensile test usually runs. And then we have cameras and vision system to measure elongation, standardized load cell to measure the force. And there's a whole bunch of other intelligence happening to kind of get you the perfect test every single time. Once the test is done, it drops off the sample in a back bucket and then continues to the next sample and the next sample and the next sample. And then obviously some software to kind of connect and collect all that data and give you some insight as well. And then when you're done, just throw out the samples and you are good to go. So quickly on machine specs, the Cube 1, the one that you just kind of saw in that video, is our first machine, was the rubber machine. So forces up to 1 kilonewton, elongation up to 1000%. So meets most everybody's needs when it comes to elastomers and silicons. I know there's some natural rubbers out there that get pretty long. In that case, it's kind of, not going to work in this. And now we have our Cube 10, our new plastic system. Same concept, tensile testing, a bit more girthy and heavier to handle higher forces, but it's made around plastics and composites and adhesive testing up to 10 kilonewtons and a bit shorter elongation.
Hey, Khaled, sorry to jump in. I think the slide is stuck on slide number 1 there.
Is it?
Yeah, sorry, I just wanted to jump in there.
No, it's a good point. Nothing, it's not moving at all?
No. Yeah, maybe if you want to go in the share, okay, there, now it's changing. It's just in the non-presenter view, I believe. So.
Oh, okay.
Sorry.
Interesting. No, it's I'll just keep it like this then.
Okay, perfect. Just wanted to let you know. Thank you.
No worries. So you guys didn't see the video or anything, I take it then? I'm gonna assume no video was seen, nonetheless. Okay, so taking a step back here, we build automated testing equipment, as I said. I'll show the video. That'll be the best kind of way to have an understanding of how the system works. So effectively, this is our machine. Hopefully this video is running. I can't really see on your end. Yeah, looks like it's running. You load up your samples, so up to 15 samples. This is our 12 tray, but up to 15 samples, tensile samples or tear samples. And effectively the machine will go down, pick up each sample separately, put it into the grips, and then pull it apart as a normal tensile sample. And then we use vision system to measure the elongation. So you see those 2 marks, it's measuring those as it gets pulled, and obviously a load cell as well to measure the force. Once that sample is done, it gets dropped off in a back bucket, and then the machine would continue through all your samples while you're not standing there doing one at a time as people usually do. Once that's completed, all that data goes into a database or your own internal or external existing database. The data can also be put in there as well. Once you're done, you just throw out your samples and it's all good to go. All right. Again, the machine specs, I think we'll be sending out these presentations afterwards so you guys can go through and kind of review and see some of the stuff that I might have glanced over and you might have missed. But effectively, these are the machine specs. So we have 2 machines, one more targeted towards elastomers and rubbers, and one more towards plastics, composites, and adhesives, and it's just more force and elongation differences than anything. There's a lot of interesting features that are inside the machine that we kind of can glance through pretty quickly. We have automated thickness, automated width, so we're trying to automate as much of the process as possible to help kind of speed up and reduce the amount of potential error. Consistent temperature, so there's a temperature system within to keep it a consistent temperature. It is not a temperature system, it's not going up or down. It's simply trying to keep everything at ambient so you can have really consistent test data. And then we have smart grips, so the grips themselves that actually hold on to the sample while we start pulling a sample They themselves can modify how much force depending on the sample itself, and there's a lot of input that we use for that. And that enables us to reduce the amount of slip, reduce a lot of the issues, and again, get more consistent and better testing data. This says automated thickness. We also do automated width for plastics and other materials, and rubber, usually you don't do that. So we've done a lot of consistency studies and accuracy studies. You can imagine when you bring in automation, people want to know how much more consistent it's going to be. And also, are you accurate? Are you the same as my current system? Which is always a good question. In terms of the consistency study we've done, we ran a lot of samples, and we still do this with control samples that we have. We send them, we randomize with customers. So there's a lot of work to kind of try to get rid of some of the potential error points that are out there to get really down to the point of saying, what is the difference between a person standing in front of a machine and running a sample and an automated system running a sample and a large slew of samples. And what you find is it's about, there's about up to 40% more consistency depending on the labs and how they run things. But that's kind of what we found across, and that's looking at the coefficient of variation when you look at sample size sets. So that was an interesting find, and I think it could be pretty important in some cases if you're doing R&D work and you kind of want to really understand what your material is doing. It can be pretty good. When it comes to quality side of things, if you want to start using machine learning and AI to kind of improve your quality systems, better data is always going to give you better predictions. So this kind of increase in consistency can be pretty important. We do have a lot more detail on this consistency study if anybody is interested. So there's papers and information behind it, but this is just to kind of give you a very high level overview of it. We've done accuracy studies. So we look at independent, we work with this independent group that essentially sends out samples every quarter to a whole bunch of labs all over North America. And then you send back the data kind of blind, and then they put you, and they show you where you stand against everybody else. And if you pass, fail effectively, if you're really outside of what everybody else is seeing. So in terms of accuracy, we've always been pretty good. Accuracy is relative, to be honest. You'll find even across different labs, there will be differences, and we always go through and try to figure out where those differences can be. So if anybody's ever interested, we also run samples for people to do the same thing. So if we get samples from customers early on in the process, we run the samples blind, give you the data back, and you can review and contrast and see how different it is or how close it is, hopefully, to the systems that you're currently doing. So yeah, I mean, quickly on the benefits of the hardware that we have, so I can get into kind of some other interesting stuff, but just as interesting. Time saved, I think that's a big one for customers when they're buying our machines and putting them into the labs. They're saving a ton of their technician time by allowing them to kind of load up samples and walk away and do something else. And it's a significant amount of time walking away that, they don't have to keep coming back every 5 minutes to tend to the system. It'll just keep going on its own. That savings is quite big when you're running hundreds of samples, even when you're in an R&D setting, when you have a limited amount of people trying to do 20 things at the same time. Consistency, obviously, increasing consistency is always good. It gives you a better idea of how your systems are working. And then additional benefits, cleaning backlogs. It's a great sales tool. It looks very different in a lab. Same with the C-Therm guys, like that. Their system looks really cool. I think that's always interesting to have something that stands out and show you're bringing innovation into your lab. Hopefully good innovation, not just innovation for the innovation's sake. And attracting young talent. So I've been seeing the industry get younger and younger, which is awesome to see that we're attracting this young talent into our industries in the rubber and plastic space. But I think, young folks want to be able to work on and work with new tech. They want to work on automation and AI. Otherwise, they will go off and work in Silicon Valley or whatever. So we are kind of always fighting for that talent. And if we want to attract great talent, I think it's important to also have great things for them to use and learn from. So that's kind of what we do as a company. We build automated testing equipment and sell it to kind of some large companies. And again, like I said, we do have companies that have been using it for years now, large and small companies alike. Hexpol's buying it for all their production plans. So it's kind of been out there and expanding for a while now. So Industry 4.0 and Lab of the Future, and I think this is kind of where we're talking about how to accelerate characterization of materials. How do you take it from the step we're at today to, an exponentially faster process? And I think it comes down to this concept of material acceleration platforms, which I'll explain in a minute. But first, let's kind of get into Industry 4.0. So there's been 4 industrial revolutions. Everybody thinks effectively we're at introducing computers and robotics is Industry 4.0. It really isn't. That's actually very old news. Imagine working with anybody today that doesn't have a computer, or you'd be quite shocked and probably wouldn't work with them. But Industry 4.0 is taking all these systems, these robots, computers, etc., and adding intelligence. And that means a layer where they can kind of determine what they need to do, modify, change. An example is, let's say your production line is running at full tilt. You have feedback on the process in terms of the end of the line. There's testing that's happening, and you see that there's a bit of a discrepancy. And your systems are measuring humidity or something, and you see the humidity is also, there's a difference. The system can self-modify to make up for that humidity difference to make sure that you're getting a more consistent output of material. That's just an example, but that's really where you're starting to add intelligence into factories, into our labs, everywhere along the process. Quickly, in terms of AI, that word is so generalized, it's a bit crazy to me. When you think about artificial intelligence, simply think of systems that predict outcomes. That's what they're supposed to do. They're supposed to predict, if I do this, this is what's going to happen. So they're really just prediction tools. They're prediction tools that work on really good data. The better the data, the better they predict things. And they might be predicting perfectly well, but the data you're giving it is garbage. So garbage in, garbage out. So they're just prediction tools. Clean data is extremely important. Clean is organized, good data. So think of an Excel sheet. If you have numbers all over the place, no headers, if you can't understand it, the system can't understand it. So that's one way to look at clean data. The other one is obviously understanding the data and making sure that it's good, clean data, that the testing went well, that it's consistent, that you don't have other errors that you're not factoring in that can skew the prediction capability of the system you're trying to build. And again, Industry 4.0, process of making manufacturing smart. So in terms of steps that you can take to kind of prepare for Industry 4.0, these are the most successful steps that we've seen so far. One is increasing automation and increasing better systems in your lab, systems that give you better, more accurate data, whether it's through automation or just better systems themselves. And that starts to produce a really high quality set of data for you to play with in the future. Improve your data collection. So we still see people where we go in and it's still on paper, it's still being printed. They still have floppy disks somehow. Some people don't even know what those are anymore, which is interesting to me. It's just the save button. But I think improve how you collect your data, whether it's cloud-based data collection. Look for the tools that are out there that are quite amazing. And there's some really good tools if you guys want us to kind of point you in the direction, and systems that people are using that are fantastic. And begin to digitize data from all your machines. Try to figure out a way to kind of connect them. In some cases, they might be too old, it might be too expensive, and it's just going to take time. It doesn't mean do everything now. But this is something to start thinking about when you're buying new equipment, upgrading equipment, or looking at new ways to kind of refresh your labs. So the more you improve that data collection, the faster you can move towards implementing kind of a smart lab and implementing AI and predictive capabilities. When you kind of get past that improving data collection, you have to analyze your data. The data part, you'll hear me say this a lot, will be 70% of the work that you actually end up doing in terms of setting up any of these projects. Because in a lot of cases, you have to digitize and you have to understand if it's good or bad data. And so we've seen a lot of customers kind of get stuck in that process because it's a really long process. So analyze and make sure you have good high quality data, remove the stuff that's garbage so it doesn't kind of skew the prediction capability, and then start by implementing in very simple projects and grow to bigger projects. A lot of people want to jump all the way to step 5, all the way at the bottom, and it's always unsuccessful, and then management gives up and everyone puts their hands up and says, AI isn't ready. But really, I think it's just people trying to run before they can walk concept. So this is kind of the most successful path that we've seen for most folks as they try to implement it across their organizations. So MAPS, material acceleration platforms. It's actually something that was coined working between Germany and here in Canada as well. And effectively, the goal is combining automation, AI, big data, all this stuff to accelerate development of materials. So you're effectively imagine a box where there's a chemist inside and a automated testing system in cells and a system that figures out what it needs to do and does it next and keeps going and going until it makes the perfect material that you ask it to do based on certain properties. It's been tested, it's been tried in a lot of academic labs. And this is an example of a map that was done. And effectively, the end result was, it was a company that started looking at light stability and the polymers they were working on. And they did it for years. This is outside of the scope of building the map. They were just running a normal company. And then they started working with accelerating, looking at accelerating the process or seeing what could have been done. It went to kind of a big project. And in the end, they built an automated lab, a map, specifically for this one project. And it went from years of development that it originally took down to weeks of development. So the step was absolutely astounding. And this is what's possible. It's expensive, it's complicated. There's a lot of technology that still needs to be built to get there. But this is what's possible in terms of really accelerating characterization. We don't have to get all the way there. We can take steps to kind of improve our process to make it better every day, but getting there is kind of the ultimate goal. And this is what really excites me, at least, and gets me out of bed in terms of what we're trying to build towards. And that kind of gets us to the cube, which is what we're trying to build around the map system. And it's effectively, the goal is to build a fully automated lab for the polymer industry and for polymer development. As you can see, kind of right now, this aspect of the whole lab, which we kind of break up into 3 sections. There's the synthesizing portion, where you're kind of figuring out what you're mixing and how much of it, et cetera, et cetera. The processing portion, so you're processing it into test slabs, into some kind of format that you can do something with it. And then there's a testing portion. Once the testing is complete, you're putting that data back into an AI database, and it figures out what to mix next, and it keeps going and going and going. And the goal is to be, 100 times, 1,000 times faster than the process we have today when it comes to creating composites, when it comes to creating green materials, when it comes to creating recycled polymers and plastics. And you can imagine as the system kind of gets going, it gets smarter and smarter. So there's projects happening all over the world and pieces on this, which is absolutely amazing to watch. Our goal is to kind of start working towards that step by step. In terms of the testing, we've built an automated testing cell, which is a project we're currently finishing up now and kind of putting together. So that's why I haven't shown it fully yet. But effectively, it's one system that can do tensile, flexure, hardness, color, and melt flow index, all in kind of a pretty compact tabletop system. And this is kind of an automated cell that can then be plugged into a future map, for example. More of an internal project that we're working on. The one thing I want to say around this is, when you look at these tests, they don't have to follow ASTM standard. This is one thing that we found that I think is very interesting. They don't have to follow ASTM standards and et cetera, et cetera. You can modify the tests, and we call them surrogate tests. So they're correlated to ASTM. But the goal here is, if you're running one of these systems, is to see the changes that are happening as you process a new polymer or potential new polymer. So this is kind of something that we've been working on as well. But this is kind of looking at the future. Our bread and butter today is kind of automated tensile testing. And that's kind of what I got. Thank you so much, everyone. I guess we'll take questions along the way or at the end. But thank you.
Awesome, thanks, Khaled. If you just want to stop sharing your screen so I can.
Yep.
Awesome, thank you.
There you go.
Alrighty. Awesome. Okay. Perfect. My name's Travis Parkman, and I'll be talking about the DMA portion of today's webinar. I'm also partly the reason why we're running a little bit late, so I apologize on that. So we C-Therm, so us at C-Therm here, we distribute Metrovid DMAs for North America. These are high performance DMAs with 50+ years of experience in industry. And a big key to this is their rigid design test frame, which unlocks an unmatched test range. And also, too, the advanced transducer network for continuous performance across different states is also really impressive. So this includes measuring a material from your glassy state down to your rubbery state, low to high strain measurements all in one test. You don't need to switch out any sensors, as well as static to 1,000 hertz in terms of frequency. So that's unusually high frequency range for DMAs, and that's partly due to the fact of this rigid test frame. You can also get direct measurements. So this includes doing nonlinear viscoelastic analysis through high strain testing, and you can measure directly up to 1,000 hertz. There's also some added capabilities. This is where the DMA Plus comes in, I guess you could say. That includes fatigue testing, hysteresis curve analysis, crack growth camera, heat buildup, and automation. So those who are not familiar with DMA, or dynamic mechanical analysis, it's a powerful tool to measure the viscoelastic properties of materials, including polymers. And viscoelastic properties are both viscous and elastic characteristics undergoing a deformation. I'll touch a little bit more on that in later slides there. And these material properties are unique to DMA. So the way DMA measures these material properties is it will apply an oscillatory deformation to a sample, and it will measure the response here. So unlike static tests, this is a constant load. So unlike static tests where a constant load is applied, this dynamic periodic load is applied in this test. And essentially you'll get a time waveform that looks something like this. Unlike elastic materials, you'll have a slight phase angle between your applied displacement and measured force, or vice versa. And I could go on and on about the equations and assumptions made, but I'll just use a simple analogy of bread goes in, toast comes out, where we don't really care what happens inside the toaster. And I'm going to assume most of our viewers today don't really care what happens in terms of the lengthy equations that give us our material properties either. So I'll just jump right to it. So from this time signal analysis, we can get our storage modulus, which refers to the material's ability to store mechanical energy and is related to the stiffness. The loss modulus, which is the ability for the material to lose or dissipate the energy, and is more related to the viscous nature or the damping behavior of the material. And then we have our tan delta, which is the loss factor, which is the ratio of these two measurements of the energy loss over the energy stored. And you can kind of think of this as a spring and damper system, where our E prime is our spring and our E double prime, or our loss modulus, is our damper. So how does this relate to fillers? That's a great question, because that's the biggest thing we'll usually see from customers is the DMA measurement is great, but how does this help me? So for fillers, there's a bunch of different ways you can use DMA. The two common ways would be temperature dependency, by doing a glass transition temperature sweep to measure the glass transition temperature with a small strain applied. This will measure the linear behavior of your material and give you an idea of how your materials change with temperature, as well as when they will transition from a rubbery state to a glass state, or vice versa. As well as strain sweeps, which measure the strain dependency of your material. This is known as like a nonlinear analysis, because it allows you to measure the linear state of your material and when you start to see the nonlinear effects of strain. If you guys are interested into more DMA techniques, I highly recommend reading Dynamic Mechanical Analysis by Kevin P. Menard and Noah R. Menard. I refer most of our customers to this book. I use it all the time as well if I ever need a little catch up. It's a great resource to have if you're doing any DMA analysis. So we used to start off with the temperature sweep. This involves either heating or cooling your material from point A to point B. And you'll get a curve that looks something like this. And the main measurement we'll want to get from this is our glass transition temperature, which is indicated by the peak of tan delta here. And this will state where our material will start to act either more glass, brittle, and hard-like, or more rubbery, soft, and like. I should mention too that the glass transition temperature can be determined by E prime, E double prime, or tan delta. It really just depends on what your application is. Tan delta is usually more of an analytical test. You'll see that in a lot of ASTM standards, where E prime is more when you want to understand when your structural properties change, since your E prime is related to your material stiffness. And just since we're talking about different methods to measure glass transition, I should mention too that you can also measure the glass transition temperature through DMA, TMA, and DSC. They all have their own benefits, and usually there's an industry standard that researchers will prefer to use. So it's probably best just to stick with what industry is doing. But I can mention with DMA is that it's one of the most sensitive methods for detecting glass transition temperatures. This includes secondary transitions in the glassy state or in other states as well. As we can see here, we're able to recognize multiple transition states of the material. And for fillers, well, fillers can modify the overall temperature response of the material. So fillers can increase or decrease the stiffness and modulus of your material in the glassy and rubbery range, depending on your application. Fillers can also increase the usable temperature range by shifting your glass transition temperature to a higher or lower temperature if you want to maintain mechanical stability for a larger temperature range. And then another useful use of the temperature sweep is as a quality control check, since poor filler dispersion and curing procedure can be identified by the shape of your tan delta versus temperature plot. And just as, oh, well, my curves disappeared here. That's not fun. But essentially what you can use for a temperature sweep too in industry is to predict how your material will perform under certain temperatures. This is this is widely used in the tire industry as a quick check. I don't have a drawing tool here, so I can't make this up on the fly. But essentially, your tan delta peak, the location of it, can help suggest whether your tire compound will be a better winter tire or summer tire here. So winter tires, they'll usually have a glass transition at around -40 or so, and while a summer tire will usually have a tan delta peak around 0 degrees Celsius. And this is just to help, and this is just related to the tire performance with relation to the tan delta here. So at -20 degrees Celsius, a higher tan delta usually suggests better winter traction. With -10 degrees Celsius, it'll suggest a higher tan delta will suggest better ice traction. And then at 0 degrees Celsius, a higher tan delta will suggest better wet traction. And then finally, at elevated temperatures such as 30 to 60 degrees Celsius, a lower tan delta will suggest better rolling resistance or mileage. This is really dependent on what your internal study is doing. Every company is a little bit different, but these are kind of the good ballpark values to follow. And just to follow that up with an example, I just wanted to go over a paper titled "The Synergistic Effect by High Specific Surface Area Carbon Black as Secondary Filler in Silica Reinforced Natural Rubber Tire Tread Compounds." And the goal of this study was to optimize the tire performance by using different concentrations of carbon black as a secondary filler in a tire tread compound. And the tire tread compound was a silica natural rubber blend. And they considered 7 different concentrations during this study. And what they did was they did temperature sweeps from -80 to 80 degrees Celsius with a high force DMA, with a frequency of 10 hertz and a strain of 0.1%. If you've attended one of our previous webinars, I kind of mentioned how every ASTM standard will have a specific frequency you can test at, usually between 1 and 5, but a lot of the times in the tire industry, you'll see around 10 to 12 hertz, and that's just to replicate the rotational motion of the tire. And what the researchers were able to conclude that 18% carbon black content provided a good synergy between the silica natural rubber compound here. And I'll kind of highlight that here, how they came to this conclusion. So they plotted their tan delta. So the plot on the left here is the tan delta value at 60 degrees Celsius versus carbon black content. And they're able to see that lower carbon black content provided good rolling resistance, or lower rolling resistance, I should say. And then measuring the tan delta at -20, they're able to see that there was a peak in ice traction performance with 18% carbon black content. And then they noticed that the carbon black had a minimal effect on wet traction. So they were able to conclude that 18% carbon black was the optimum content for their material. Another way I mentioned earlier is you can do strain sweeps to measure the nonlinear performance of your materials. So that includes dynamically straining a sample at one amplitude and measuring the viscoelastic properties, and then incrementally increasing this as the plot shows here. And what this will do is, it's a little bit different than most DMA tests. Most DMA tests, you'll want to do it at low strains. But when you apply high dynamic strains to your material, you're breaking the filler to filler interaction, and you're changing the material properties. So a strain sweep is designed to understand how your filler interactions break as a function of strain. And I should mention too that this is known as the pain effect and is assumed to be reversible, as the bonds will recover and reform once the large strains are removed. And here's just a plot showing how this will look here. So we can see here that we have our linear region at the start at the small strains on the left of our plot. This is where the storage modulus will remain constant. And then after a while, after incrementally applying larger and larger strains, we'll start to enter the nonlinear viscoelastic region. And this is where we notice that the stiffness or the modulus begins to decrease with a steep slope. This is one of the benefits of a high force DMA, is that you're able to apply enough strain to your material to measure this. I just took a quick snapshot of this test, and you needed about 85 newtons peak to peak to be able to strain this material to get into that nonlinear viscoelastic range. I should also mention too that the pain effect is highly dependent on temperature, so executing this test at different temperature stages is very important, and that this is amplified, especially when you're near the glass transition temperature. And just to touch on a final note here, Cal did a great job talking about automation and about how valuable it is. And I just kind of wanted to touch on that a little bit too with Metrovib's solution for automated testing, which is known as the Expander. It's a 6-axis robot designed as a flexible automated solution. So it allows you to do automated shear, tension, or compression tests in DMA. You can run your test 24/7 with a 12-rack carousel. And I do mean that when you can run this machine 24/7. We have many customers that will go in on Monday, load up their samples, come back next Monday, and have all their results. And this pairs really nicely with the text alert status, where you can be alerted if the machine goes down, someone bumps into the robot, or if there's a power failure in the system, you can get notified so you're not babysitting the machine as well, because that kind of ruins the value of automation. And then it can also improve the accuracy by reducing user error. And I'll mention that too in my next application note. And just to touch on how the robot works, it uses air suction to grab test samples. So it can now grab any irregular shaped samples as well. This includes small samples like O-rings, finished samples as well, as long as a suction head can grab the material, you're able to test it with this machine. And the robot will tighten your sample the same way every time. This includes orientation and tightness, reducing the user-to-user error. And your robot head opens and closes the thermal chamber, moves the carousel, so there's little intervention. Once you hit play, you let the machine do the rest. And just to kind of touch on a study here, an internal study that Metrovib did, I think Cal did a great job of mentioning how accuracy or automation can improve accuracy, not just efficiency. And this was something too that Metrovib wanted to show. So what they've seen in the past is with manually loading samples, you can have a couple easy mistakes. Your sample can be buckling, it can be rotated a little bit, it could be off center, as those pictures show there in a pretty extreme fashion. I hope no one's loading their samples like that. But even the smallest inconsistency in loading can affect your sample stiffness, which affects your measured modulus. One of the big benefits of the Expander is that you're loading the samples the same way every time. So you're eliminating user-to-user variance as well as day-to-day variance, which just comes with us being humans. No one's perfect. We feel a little bit different every day. I mean, I don't know if you can hear me sniffling right now, but I'm sick as a dog right now. So we all feel a little bit different every day. So performance is never perfect, but with the Expander, you help eliminate that error. So with their study, Metrovib tested 20 samples the first step was to test the same sample 20 times with no loading or unloading effects, just to see what the standard kind of expected deviation would be. So this is with the same sample, not interacting with it, just running the same test 20 times. They notice a very small standard deviation in their measured material properties, which is expected. And then they repeated this with loading and unloading the samples with the expander. And even though there was a larger standard deviation in the measured properties, it was still very small, less than 1% in standard deviation. I should mention too that the expander robot was loading and unloading the same sample every time, just to reduce the effect of inconsistencies in the material, just to really focus on the loading and unloading effect. And that's the end of my portion here. Just in conclusion, DMA can be used to evaluate and optimize filler performance via temperature or strain sweeps, and automation improves the efficiency and testing accuracy. Also be doing the outro today. So if any of this content was of interest for you, please go to our website at www.ctherm.com. We have all our webinars, including this one, as well as our tech library featuring publications. If there's not something on there, you can always reach out to us as well. We're always happy to provide more content. And speaking of content, our next upcoming webinar is STA 101 Fundamentals and Application, focusing on phase change materials, February 29th, by my colleague Hitoshi. Should be a very good presentation. And then follow us on LinkedIn for other future webinars, content, if we'll be at other shows. We're usually publishing stuff on there every day, so we're pretty active on there. And then this comes to the question portion. Thank you for all attending today. I think the recording's going to end, but we're just going to stick around and answer some questions.